So let's do some sample problems for Newton. So question 1 is thinking questions. So let's go through those. If the distance between two objects doubles, what happens to the force of gravity between them? So remember, we're thinking of the equation Fg equals Gm1 m2 over r squared. And so it says the distance between the two objects double. So I'd put a 2 here. Notice there's a square right there, right? And so that means that would be the same as this whole equation as Gm1 m2 over r squared with a 1 over 4 in the front. So the answer would be the force would go down by a fourth. So it would go down by 4, down 1/4 is big, times 1/4, whichever way you want to look at it. I kind of like looking at it as times 1/4. And the next one says, if the distance between the two objects triples, what happens? Well, we saw when it doubles, it was the square of 1/2, right? So we took 2, we flipped it over, we got 1/2, we squared it, we got 1/4, right? So now it says triples, so I'm going to take 3, I'm going to flip it over, that gives me 1/3, I'm going to square it, that's going to give me 1/9. So the answer here is going to be 1/9, so times 1/9 will be the answer for the second part of number 1. And this says if the distance between two objects is halved, okay? So now if we're doing half, we take 1/2, we inverse it, so we get 2, and then we square it, so we get 4. So that means it'd be times 4 for that one. And then if the force of gravity to objects is tripled, how is the distance change? Oh, so now we got to do it backwards. So we're starting from over here, right? And we're going backwards. So let's think of that backwards. So first, if it says that it's tripled, I got to take the square root, right? Because the opposite of square is square root. So I'm going to start with a 3, and then I'm going to square root it. So it's going to be the square root of 3. But then, right, I have to go and flip it back over. So it's going to be 1 over the square root of 3. So it's 1 over the square root of 3 times this big. So it's going to get smaller. The distance has to get smaller because it tripled, right? It had to go up, right? They're inversely related. Whatever you do, it does the opposite. So the force and the distance are opposite of each other. Okay, so that's number 1. Number 2, we get to do 5 steps. So it says 2 alien astronauts are in deep space. Zordon has a mass of 6,000 kilograms, while Ufda has a mass of 2,500 kilograms. They are 3 meters apart. What is the force of gravity between them? Okay, so we go given, and we say M1 equals 6,000 kilograms, and M2 equals 2,500 kilograms. And we always know big G, because remember, G is the same everywhere, so that's 6.67 times 10 to the negative 11th kilograms meters squared per... No, that's not the right units. Let's check that again. It's the right number. It's newtons, right? So it should be newtons meter squared per kilogram squared, right? Okay. So we're trying to find Fg. That's a question mark. And so we know it's green M&Ms R squared. So Fg equals green M&Ms R squared. It's already solved. Cool. So now we plug it in. So Fg is equal to 6.67 meters squared per kilogram squared. I don't know why I don't want to remember that Newton. The Newton should be up there. And then times 6,000 kilograms. We're running out of space here, so I'll have to do it on top. Times 2,500 kilograms. And that's all divided by 3 meters squared. Yeah? So then we plug it in, up a little bit, and what do we get? Pull out my handy dandy calculator, and we do 6.67 times 10 to the negative 11th, and then times 6,000, and then times 2,500 equals divided by 3 times 3, which is 9. So that comes out to be a very small number, 0.00011 newtons, right? Or I guess we could write it as 1.1 times 10 to the 1, 2, 3, 4, 10 to the negative 4th newtons, right? Why is it such a small number? Does it make sense? Well, yeah, it makes sense because look at this. This is 6,000 and 2,500. I mean, those are really small masses. Remember, you have to be huge to get much gravity going. So our Earth is much, much, much bigger than that. So that does make sense. Good. Let's try the next one. So the next one says, the mass of a planet Anasis is 7.2 times 10 to the 25th kilograms. So look, that one's big, like Earth. And it is 4.06 times 10 to the 8th meters away from its nearest moon, from center to center. The force, that means it's its orbital radius. The force of gravity between the two bodies is 9.3 times 10 to the 14th newtons. So now it has lots of force. What is the mass of Anasis' moon? Okay, so let's start with our givens. And we can see 1, 2, 3 values for our given. Kilogram, this one's meters down here, right? So kilograms is mass. So we have M1 is 7 equals 7.2 times 10 to the 25th kilograms, right? Kilograms. And then meters, this one here, right? Meters. Meters is R, so R is 4.06 times 10 to the 8th meters. That's a point in there, didn't show up very well. And then this last one is Newton, so I know that's 4. So FG equals 9.3 times 10 to the 14th newtons. And then we always know G. So G is 6.67 times 10 to the negative 11th. I'm trying to write 11, really I am. 10 to the negative 11th, and remember it's newtons meter squared per kilogram squared. Right? And we're trying to find the mass, right? So we're trying to find M2, the other M. And we know our equation. It's got to be green M&Ms because we're dealing with gravity. That's, if we write it right, it's going to be FG equals GM1 M2 over R squared. 2. All right, so GM1 M2 over R squared. We want to solve for M2, so that means I'm going to multiply both sides by R squared, so I can cancel off the R squared, and then I'm going to divide both sides by GM1 divided by GM1, and so that cancels out the GM1. So in my solve step, I end up with M2, right, because that was the only thing left over here. So M2 is equal to R squared FG, all divided by GM1. Not that bad, but that's where we're at. So we're going to move this up a little bit so I have a little space, but I might be able to see my givens. Let's keep it there. Looks good. So now I can go M2 is equal to, what was my R? 4.06 times 10 to the 8th meters squared times FG, which was 9.3 times 10 to the negative? Was it really negative? It was positive. I don't know why I had a negative there. It should be times 10 to the 14th, right? 9.3 times 10 to the 14th. Just double checking. So let's get rid of the negative. It was definitely not negative. It should be, oops, let's get rid of the negative here too. Times, I was going to say that's really tiny. Times 10 to the 14th newtons, right? And then we're dividing by G, 6.67 times 10 to the negative 11th newtons meter square per kilogram squared. And then that's all times m1. Oh my goodness, we're going to have space. 7.2 times 10 to the 25th. 10 to the 25th. All right, gotta scoot over just a little bit. 10 to the 25th. 10 to the 25th, and that was kilograms. All right. So let's try plugging it into our calculator. This is one I would suggest you do the top and then do the bottom. So let's do that. And so I'm going to do the top. So it's 4.06 times 10 to the 8th, and that's squared. And then times 9.3 times 10 to the 14th. So that gives us 1.6. We can round. 1.6 times 10 to the 32nd on the top. We'll check units in a second. And on the bottom, we've got 6.67 times 10 to the negative 11th, and then times 7.2 times 10 to the 25th. Oops. Mine, instead of doing a parentheses, did a number. Okay, so that comes out to be 4.8 times 10 to the 15th. So then I plug those in. So 1.6 times 10 to the 32nd divided by 4.8 times 10 to the 15th, which is equal to 3.3 times, still a pretty big size mass, right? 10 to the 16th, but it's a moon. Kilograms. Now, it should come out kilograms. So let's just double check our units so we're sure we did this right. So we're going to look at our units up here, and we see meter squared cancels out with meter squared. And then we've got 1 kilogram that canceled out with 1 kilogram. The Newton canceled out with Newton. This kilogram's on the bottom, so it comes to the top. So that's where we get this kilogram, and it works. Awesome. We're done.